This slide shows a scope plot of complete scanning cycle. First, the channel is discharged so that we can start from 0 volts. Then the CTMU starts charging the sensor for a fixed time. Then the ADC converts the charge buildup. Note that the voltage buildup has a discharge slope due to high value of oscilloscope probe leakage. Typically, CTMU can scan a channel in 6 microseconds. This enables to service a large number of capacitive touch buttons in an application. Also, this allows bandwidth for other applications to run in conjunction with the capacitive touch on the same PIC microcontroller. When the sensor is untouched, the charge buildup is higher than when the sensor is touched. ADC measures the voltage and the firmware detects the sensor is being touched or pressed. So in this slide we are showing two different scope plots of the sensor being touched and untouched. The same concept can be applied for proximity sensing. Basically, the firmware differentiates a varying ADC value when a proximity is sensed. There are many other applications the CTMU can be applied to. Some of them are listed here. First is time domain reflectometry, uses the time measurement side of the CTMU. Second is temperature measurement using a simple diode. We will see these two applications in the next section. Third is a humidity sensor, is nothing but a varying capacitance, and CTMU is perfect to measure the variance in capacitance. Also, CTMU can be used to measure absolute capacitance and relative capacitance change, as shown in capacitive touch sensing application. Also, it can be used as digital to analog converter or DAC. We will see the TDR or time domain reflectometry and temperature sensor applications in detail in the coming sections. First, let us see what the time domain reflectometry or TDR is. In layman terms, TDR is basically time taken by a pulse to propagate through a circuit and to reflect from the end of the circuit back to the source. In example of a coaxial cable that has 50 ohms, it is typical time domain reflectometry. TDR has long been used to measure the electrical length of transmission lines, locate faults in transmission lines, and characterize transmission line impedance. The figure shows a pulse generator with resistance R0 connected to a transmission line with impedance Z0 and a termination resistance of RT. If we use the occurrence of the rising edge of the pulse as a reference point in time 0 nanosecond, then at t is equal to 0 nanosecond, the voltage at node A is equal to Vp multiplied by Z0 divided by R0 plus Z0, where Vp is the amplitude of the pulse. The transmission has an electrical length of T0, where T0 is the time it takes for the pulse to propagate down the transmission line. The electrical length T0 of the transmission line can be calculated by taking 1 over the speed of the light, or which is equivalent to 1.017 nanosecond per foot multiplied by the length of transmission line. The voltage at node A at 2 times T0 will be Vp multiplied by RT divided by RT plus R0. So if the transmission line is unterminated, Va is equal to Vp when T is greater than or equal to 2T0. The scope plot here shows a pulse generator with a 50 ohm output impedance driving a 2 volt pulse into an unterminated 50 ohm coaxial cable. So using this we can determine the length of the cable. The two-step waveform shown here is of an unterminated transmission line as shown in the scope plot here. The initial voltage at t equal to 0 nanosecond using equation at node A is 1 volt, which is nothing but Vp over 2. At time 2t0, the reflected pulse from the unterminated transmission line returns, and using the second equation, the voltage at node A is 2 volts, which is equal to Vp, which is the voltage of the pulse. So the time domain refers to the fact that we are looking at the waveform in the time domain, and reflectometry refers to the fact that we are looking at the reflected impedance of the transmission line and transmission line termination. The impedance is represented by the voltage in this case. Next, let us see how CTMU can be used to measure temperature using a diode. An inexpensive way of measuring temperature is using a diode. The forward voltage drop of a diode varies with the temperature. With this theory, using common diode and constant current source on CTMU and using A to D converter on microcontroller for measuring the forward voltage, temperature can be measured to an accuracy of 1 degree Celsius. This slide shows how temperature can be sensed using CTMU and a diode. The equation shown here defines the forward current of a diode as factor of forward voltage and temperature. When forward current is constant, most other components are constant other than the temperature and the forward voltage. By measuring the forward voltage, temperature can be determined. As shown in the block diagram, CTMU powers the diode with a constant current source, and the ADC measures the forward voltage of the diode, and temperature is proportional to forward voltage. This graph shows the data for a commonly available rectifier diode 1N913. X-axis is the temperature and Y-axis shows the A to D converter reading, with 64 samples accumulated in this case. As you can see here, the ADC reading varies more or less linear to the temperature. This gives an inexpensive way of measuring temperature using CTMU and a diode. There are many resources available from Microchip for CTMU and capacitive touch sensing application. First, refer to the family reference manual. The number here is DS39724. Second is a demo board called the PICDEM TouchSense 2 demo board, which demonstrates CTMU in capacitive touch sensing application. Third is visit www.microchip.com/mtouch for update and all related collateral. There are more than 20 PIC microcontrollers with CTMU and many more are following. As I mentioned in the earlier slide, the PICDEM TouchSense 2 demo board DM164128 demonstrates CTMU in capacitive touch sensing application. This board has implementation of direct keys, matrix keys, and linear slider. Also, this comes with a free graphic user interface for diagnostic and customization purpose. Using this graphic user interface, you can customize your own capacitive touch sense application. Please refer to the documentation by visiting www.microchip.com/mtouch. So this concludes this webinar. To summarize what we discussed so far, we have seen the key features and detailed block diagram of CTMU and how to use CTMU for capacitive touch sensing and TDR or time domain reflectometry, and how to use CTMU for temperature measurement application are discussed in this webinar. Also, the resources available from Microchip are discussed. With this, we conclude this webinar. Thank you for watching this webinar. Hope you find this helpful. Thank you.